This is a visualization of the Cabibbo-Kobayashi-Maskawa, or CKM, matrix. It describes how quarks change flavor under the weak interaction. To comply with the standard model, its top row must adhere to strict unitarity, meaning the sum of the squares of these elements must equal exactly 1. To prove this unitarity holds true, physicists must calculate the value of the first element, VUD. That calculation depends heavily on a single physical variable, the exact decay rate of the free neutron. If that measured lifetime deviates slightly, the top row fails to sum to unity, indicating a fundamental gap in our understanding of the weak interaction. Determining exactly how long a neutron lives is a rigorous test of the mathematical symmetry holding our universe together. This scatter plot maps historical measurements of the neutron's lifetime. Over the decades, physicists improved their instruments, shrinking the error bars and seemingly zeroing in on a precise consensus. But as precision peaked, the modern data suddenly split into two distinct, non-overlapping trend lines. They are separated by a stubborn, vertical gap of approximately 10 seconds. Multiple independent audits have ruled out known systematic errors. This 10-second gap remains strictly persistent across different high-precision facilities. Instead, the data correlates with the physical architectures used in the experiments. One measurement comes from trapping the particles in a confined space, and the other comes from measuring them in flight. Deconstructing the engineering between these two methods is our best tool for determining if this gap is a mechanical blind spot or the signature of dark sector physics. The in-flight measurement happens here at the National Institute of Standards and Technology. This is the home of the Beam Lifetime, or BL3 experiment. This layout shows BL3's mechanism, a continuous beam of cold neutrons traversing a vacuum cylinder. Overlaid is a penning trap. Some neutrons beta decay, emitting a proton. These positive protons curve sharply into the magnetic trap, while surviving neutral neutrons pass cleanly through. Physicists calculate the lifetime by comparing the total flux of traversing neutrons against the exact number of trapped protons. The BL3 architecture calculates lifetimes strictly by counting the charged debris created by the decay. It is a measurement of particle appearance. The opposing measurement comes from the Los Alamos National Laboratory. This is the site of the UCN tau experiment, utilizing the bottle methodology. This experiment uses ultra-cold neutrons. Their kinetic energy is so low they cannot penetrate magnetic boundaries, allowing manipulation by entirely invisible repulsive walls. This cutaway reveals the UCN tau vessel. Its walls are lined with a Halbach array of permanent magnets, generating an upward levitation field. Combined with Earth's downward gravity, the device effectively suspends the neutrons, confining them in the center without ever touching a physical wall. After loading the trap, researchers wait for a precise time interval, then count the surviving neutrons. Unlike the beam method, this bottle architecture ignores the decay debris. It strictly tallies what survives. It is a measurement of particle disappearance. These two counting metrics, proton appearance in the beam and neutron disappearance in the bottle, create a critical vulnerability in the data. Consider a dark sector decay. What if a neutron doesn't decay into a visible proton, but instead vanishes into an invisible dark matter particle? This maps the dark decay hypothesis. Left, in the BL3 beam, a neutron vanishes into dark matter. With no proton, the counter stays at 0. Right, in the UCN tau bottle, the same neutron vanishes. The survival counter correctly ticks down by 1, accurately logging it. This 10-second data gap matches the exact architectural blind spot expected if 1% of neutrons are quietly leaking into the dark sector. The strict magnetogravitational trapping principles perfected in UCN tau are now being scaled to hunt for other theoretical variables, including the absolute mass of the electron neutrino. This schematic details Project 8. It uses a similar Halbach array to confine incredibly cold atomic tritium. To extract data, physicists overlay a specific magnetic field topology for cyclotron radiation emission spectroscopy, or CRES. When the confined tritium decays, it emits a beta particle. The CRES topology isolates this electron, precisely measuring its exact kinematic endpoint energy based on the cyclotron radiation it releases as it spins. By capturing the absolute kinetic energy limit of the visible electron, physicists can run the kinematics in reverse and mathematically deduce the exact missing mass of the invisible neutrino. This spectrum visualizes the neutrino mass hierarchy. Project 8 is designed to reach an unparalleled sensitivity threshold of 40 millielectronvolts, giving it the required resolution to cover the inverted mass range. Simultaneously, other exotic topologies are adopting these methods. The Ariadne experiment is using polarized helium-3 NMR modulation to hunt for axions. Across all of these experiments, the unifying challenge is isolating particles from environmental interference with uncompromising architectural precision. These measurements provide the empirical bounds for T and CP violation, the fundamental symmetry breaks that physicists use to model the early evolution of matter. The resolution to these fundamental questions now relies on the precision of our laboratory architecture.